Hello everyone. In this section, you're going to look at a method called Newton's method, which can be used to approximate solutions to equations that are not easy to solve. So for example, if you're asked to find the roots or the solutions of these types of equations, they're not easy to do. So then the question is, can we at least approximate the solution to these equations? And the answer is yes. And the method we're going to look at in this course is called the Newton-Raphson method, or simply Newton's method. So here's the idea. Suppose that your function looks like this, and you want to find the root of this function, which is here. So what you're going to do is make an educated guess as to what the root might be, and we call that guess x1. Then go to the corresponding y value, which is here, and draw a tangent line at that point. Where your tangent line meets the x-axis is going to be a more accurate approximation to the root r. So x1 was here, and x2 is now here, which is closer to the root. And then you just keep going depending on how accurate you want your approximation to be. So if you want to find the next approximation, you go to the corresponding y value of x2, draw a tangent line there, and where it crosses the x-axis is your next approximation to your root r, and so on. You can just keep going like this forever. And the idea is that in general, if you keep doing this, you're going to get to a better and better approximation to the root r. We're trying to find the solution to the equation f of x is 0. Right? This is the point when the y value, which is also equal to f of x, is equal to 0. But another way of looking at that is we're trying to find the x-intercept of this curve. At least we're trying to approximate the x-intercept of this curve. In other words, Newton's method will be used to approximate the root r of the equation f of x is 0, also known as the x-intercept of that function. So let's summarize what Newton's method does. Start with your first approximation x1, and it must be an educated guess, so it must be kind of close to r. We'll figure out how to do that with an example later. So in this case, this is your educated guess that's near the x-intercept, r. The next step is to go to the curve whose x value is x1, that's here, and then draw a tangent line going through that point. Now, the x-intercept of that tangent line is called x2, and that's an approximation to the x-intercept of your curve. Let's write that down here. The x-intercept of the line L, which is in pink here, and that x-intercept is labeled x2, is a better approximation to the x-intercept r of the curve. And just keep going. So actually, let's try this next step. If you want a better approximation than this one, go to the point with the x value of x2 on the curve, that's here, and draw a tangent line. And wherever it crosses the x-axis, meaning the x-intercept, is your next approximation to the x-intercept of the curve r, and we call that x3, and so on. And notice that you've gotten even closer to the root r than you did before. The more iterations we do, the more accurate the approximation to r we obtain. So now what we need to do is express Newton's method as a formula. In other words, given x1, what will be the formula for x2? Given x2, what will be the formula for x3, and so on. Well, let's start with the equation of this line, which is the tangent line at x is x1. Well, we all know that the equation of a line can be written like this, and we also know that this line goes through the point x1, comma f of x1, where x1 is your initial approximation, and its slope is f prime of x1. the derivative at x1. So we have a point on the curve and the slope of the line. So we can find the equation of this line. It's y minus f of x1 is f prime of x1 times x minus x1. So remember, our next approximation, called x2, is just the x-intercept of this line. Let's write that down first. So the x-intercept of L is called x2. So what that means is this line goes through x2 comma 0, which is this point here. So this equation should be satisfied if you plug in x2 for x and 0 for y. So let's do that. Let's plug in 0 for y and x2 for x. And now we're going to solve for x2. That'll give us a formula for x2 in terms of x1. We have minus f of x1 is f prime of x1 times x2 minus f prime of x1 times x1. And to solve for x2, why don't we bring this onto the left side? So we get f prime of x1 times x2 on this side, and that's equal to minus f of x1 plus f prime of x1 times x1. Now, assuming that this is not 0, we can divide both sides by this to solve for x2. When you do that, you get x2 on the right side and minus f of x1 divided by f prime of x1 plus just x1, because the f prime of x1s will cancel out when you divide. In other words, x2 is x1 minus f of x1 divided by f prime of x1. So we figured out a formula for finding x2. And if you want to find x3, what you do is just replace all the x1s by x2s. So let's write this down. x3 is simply x2 minus f of x2 divided by f prime of x2, and so on. So if you wanted to find xn plus 1, that's simply xn minus f of xn divided by f prime of xn. Of course, we require this, right? Whenever you're dividing, you need to make sure that that's not 0. So this is Newton's method formula. It's a very simple formula that can be used to find the next iteration of your approximation to the root of your function. All right, so let's try an example. Show that this function has a root in the interval from 0 to 2. So for this example, we're not going to use Newton's method right away. This is actually a review of something else you've learned earlier in the course. Show that there is a root. That's the intermediate value theorem. Right, so remember, if your function is continuous on this interval and f of 0 and f of 2 have different signs, then there's got to be some x value in the open interval from 0 to 2 for which the y value there is 0. So let's first figure out the y values at the endpoints here. F of 0 will be 0 to the 6 minus 2, or negative 2. And f of 2 is 2 to the 6 minus 2, which is 62. Let's plot those points. So f of 0 is negative 2, means it goes through, let's say, around here. And f of 2 is 62. We'll not do this to scale, but let's say this is 62, so it goes through here. Now, this is a polynomial, so it's continuous everywhere, meaning to go from this point to this point, you should be able to draw that curve without lifting your pen. And when you do that, there's no way to go from here to here without crossing this line. It could cross it just once, or it could cross many times, but the point is that it must cross at least once, which means there is at least one root in this interval. So let's write that all down. Since f is a polynomial, its graph must be continuous on R. This means that the graph of f must cross the x-axis somewhere in this interval. In other words, there's some point in here for which f of x is 0. So that was the intermediate value theorem. Now, the next part is going to ask you to approximate the root of this function using Newton's method. For this one, I'm giving you the initial approximation, and 1 is a good choice in any case because 1 is within this interval. In fact, it's right smack in the middle there. So if there's a root here, then choosing 1 would ensure that you're pretty close to the root. So to do Newton's method, remember this was the formula for it, you'll need the derivative of f. So the derivative of this, which is simply 6x to the 5. And let's see what x2 looks like. Remember, x2 just means plug in 1 wherever you see n on this side. So we have x1 minus f of x1 divided by f prime of x1, which is 1 minus f of 1 divided by f prime of 1. And that's 1 minus f of 1 would be 1 to the 6 minus 2. And then divided by f prime of 1 is 6 times 1 to the 5. And that's 1 plus 1 over 6, which is approximately 1.1666 repeating. Now let's try one more because the question is asking you to do 2 iterations. So here's one iteration. One more is x3, which is x2 minus f of x2 divided by f prime of x2. And that is, I'll use the fractional value of x2 to make our x3 as accurate as possible. So since this is the same as 7 over 6, let's use that. 7 over 6 minus f of 7 over 6 divided by f prime of 7 over 6. And you can show that this is approximately 1.12644 and so on. And that's all you need to do for this part. For this particular function, it's easy to find the x-intercept. If you set this equal to 0, which I've done here, then x to the 6 is 2, which means x is simply plus or minus the 6th root of 2. Since we started with the guess of a positive number, you're going to go towards the positive 6th root of 2, which is approximately this. So I'm going to erase the negative part for this particular case. And just notice that we are indeed getting closer and closer to this number as we keep doing the iterations, right? We started with 1, which is already pretty close to this number, but x2 is even closer to this, and then x3 is even better. And you can imagine the farther you go down this list, x4, x5, and so on will get you a closer and closer number to this one. All right, let's try another one. Approximate the root of this equation, cosine x is x, using Newton's method. This is not easy to solve, but we can use Newton's method to approximate the solution. This one is asking you to just do one iteration, meaning just find x2. And it is not telling you what to use for x1, so you have to make an educated guess for that. So remember, before we do anything, what Newton's method does, it approximates the solution to the equation f of x is equal to 0. Right? It's not f of x is equal to x or f of x is equal to x squared. It always has to have a 0 on one side. That's not what's happening here. We have cosine x is equal to x. So what you're going to do whenever you have something like this is bring everything onto one side. And whatever is on the other side of 0 is going to be your function f of x. So for this case, you're going to let f of x be cosine x minus x or x minus cosine x. It doesn't matter. But the important part is that you need to make sure that one side of that equation is 0. So I'll do cosine x minus x. So then what Newton's method will do is it'll try to approximate the x-intercept of this curve. In other words, when is this equal to 0? Remember, this is your Newton's method formula. So let's find the derivative of this, which is negative sine x minus 1. Now, for your educated guess for x1, which must be close to your actual root, you can draw the graph of cosine x and x. I've done that down here. Here's your cosine x, here's x. What we want to know is we want to know where they intersect, right? Where those two y values are equal. Well, it seems like it's around here. We don't know exactly where that is, but we can see that that's somewhere between x is 0 and x is pi over 2. And pi over 2 is a little bit bigger than 1. So why don't we just pick 1 as our x1? It's in your best interest to choose an easy number for x1. So we're going to choose x1 is 1. And let's find x2. Remember, that means it's x1 minus f of x1 divided by f prime of x1. And since we chose x1 to be 1, we have 1 minus f of 1 divided by f prime of 1, which is 1 minus cosine 1 minus 1 divided by negative sine 1 minus 1. And making sure that your calculator is in radians mode, these are all radians, you're going to find out that x2 is approximately this. And since the question just asks you to do one iteration, that's the end. You don't have to do anything else. But just so you know, the actual solution to this equation looks something like this. Again, we've gotten closer to this number by doing an iteration here, right? Compared to 1, we have a much better approximation to the root. And again, if you wanted a better approximation, you would keep going, right? Find x3, x4, and so on. So that's the end of 4.8. Nice and easy. So here are some questions for you to try. You will need a calculator for these questions. Thanks, guys.